Do you remember last time we had stuff like this and we broke it down with perfect squares? So 20a squared b to the third. We've set up two radicals where like a perfect square and 20 is 4. So we put the 4 there and it's 4 times 5. 5's not perfect. And then the exponents, remember it just has to be even to be perfect. So a squared, that's all gravy. B to the third, ooh, we could put 2 there. And then 1 goes in the leftover pile. When we square root 4, we get 2. Square root of a squared, a to the first. Square root of b squared, b to the first. We got our root 5b, and that is beautiful. Oh, this one's just letters. Better have an even exponent if we're putting it in the perfect radical here. A to the third, well, 2 of them are perfect. B to the fifth, 4 of them are perfect. C to the third, 2 of them are perfect. Square root of a squared, a. Square root of b to the fourth, b squared. Square root of c to the second, c. And then you got your root a, b, c. Oh, 1, 2, 3. You and me are simplifying radicals. You guys know that song? All right, here we go. Multiplying radicals. You can multiply the numbers in the radical with other numbers in the radical. You can multiply numbers outside the radical with other numbers outside the radical. If you want, on A, you can break down each one individually and then multiply it together. That'll work. I'll show you that way, and then I'll show you the other way too. If you're looking at 8 and you're like, hey, that's 4 times 2. And 12 is 4 times 3. And then you're like, all right, so square root of 4 is 2, so we have 2 root 2. Square root of 4 is 2 times 2 root 3. Now here, I just said it earlier, you can multiply the numbers outside with the other numbers outside. 2 times 2 is 4. You can multiply the numbers inside with other numbers inside. 2 times 3 is 6. 4 root 6. There are no more perfect squares in 6, so you would be done. Here's another option. You could just multiply 8 and 12, and you get 96, and then you could break that down with perfect squares. And you might be like, oh, well, that's 16 times 6. Square root of 16 is 4. You get 4 root 6 that way. Same answer. Here's a nice little shortcut I've learned over the years. If you have the square root of, let's say, 7 times the square root of 7, that would be the square root of 49, and the square root of 49 is 7. So if you have a square root of 7 times the square root of 7, it ends up being regular 7. If you have the square root of 31 times the square root of 31, it ends up being 31. If you have the square root of smiley face times the square root of smiley face, it's going to come out to smiley face. So thinking about that, when I did it the first time, if I had a square root of 4 times the square root of 4, that's just going to work out to regular 4. And then we just have root 2 times root 3 gives you root 6 that way too. You're like, all right, that wasn't really saving me any time. I'll show you problems later where that could be the case. Or I'll show you right now. As a matter of fact, let's say you had root 21 times root 14. And you're like, I don't want to multiply those together and get a huge number. Neither one of them has a perfect square. If only there was another way. Well, think of a number that they have in common. That could be 7, right? 21 is 7 times 3. 14 is 7 times 2. And then you can do that trick I just told you. The square root of 7 times the square root of 7 is just regular 7. And then you have the square root of 3 times the square root of 2, that's root 6. That's the way I like doing those pretty complex ones like that. I think it's helpful. Or if you had the square root of 55 times the square root of 66. Can you think of anything that goes into 55 and 66, even if it's not a perfect square? 11 goes into those, right? So 55 is 11 times 5. 66 is 11 times 6. And then you could be like, oh, the square root of 11 times the square root of 11 is just 11. And then we have root 5 times root 6 is root 30, baby. Truly, that's the way I like doing it when the numbers get pretty complicated like that. I like to see, is there anything they have in common? But a lot of times, the ones we're going to have are lots smaller numbers, so it's almost easier to just go ahead and multiply them. So if we're doing b, I can do the 3 times 4, that's 12. And in the radicals, we have 2 times 10 is 20. B times b is b to the second power. So now we just have to simplify this. A perfect square in 40 is 4, or sorry, 20 is 4. It's 4 times 5, and then b squared is perfect. 12 times the square root of 4b squared is 2b, or not to be. Oh gosh, I don't know how I do it, folks. And then we can just multiply the 12 times 2b, that's 24b, or 24 not to be. Right. And then you got your root 5. You know what's crazy? One person's going to watch this video in like 5 years. They'll be like, I like that 24b joke, or not 24-2b. I'll be like, what are you talking about? I made that video when I was still in my upper 50s. And now I'm 86 years old. Oh! This works perfectly with that little trick I was showing you, the square root of smiley face times the square root of smiley face. Because I know that 13 goes into 52. If you think of a deck of cards, there's 4 sets, and each set has 13 cards. So 52 is 13 times 4. So if I think of it like that now, the square root of 13 times the square root of 13 is just regular 13. And then the square root of 4 is 2. What? So it's just 13 times 2, which is 26? Come on. Come on. Too fun. All right. If I multiply these together, we'll have 5 root 18c squared. A perfect square in 18 is 9. It's 9 times 2. And then c squared is perfect. 5 times the square root of 9c squared is 3c. And then we'll just multiply it by the 5 that was already out there. That's a 15c root 2. You know how it is. The old 15c root 2. Oh, wow. Whoa. Check this out. If on that one, you were like, oh my gosh, 3c goes into 6c. Check this. 5 root 3c times, let's make 6c 3c times 2. Oh my gosh. Then you're like, square root of 3c times the square root of 3c is 3c. And then 5 times 3c root 2 is 15c root 2. Look at that. Same answer, different way to do it. I'm so glad we're learning all these options. All right, let's see if we can do this one. Gosh, 2 great jokes in the same video. I don't know how I do it, folks. If I was doing the numbers outside, 2 times 6, no big deal, that's 12. Inside, 5 times 10, 50, no big deal. A squared times 8 to the third, that's 8 to the fifth. Look at that. Let's break it down with a perfect square. Perfect square in 50 is 25. 25 times 2 is 50, right? We agree with that? Now, a to the 5th, not perfect, but a to the 4th certainly is. And then we'll have that 5th one in the leftovers. 12 times square root of 25a to the 4th is 5a to the 2nd root 2a. Last thing we got to do is multiply this stuff outside. 12 times 5a squared would be 60a squared root 2a. And we're having fun. Learning a lot. Simplifying radicals. Having fun. Now, we've kind of touched on this when we were solving quadratic equations. When you square root a fraction, you just square root each part. So if you look here, the way it's written, it's under 1 square root, but it is the same as if they were under different square roots. So if it helps, list them separately. Or if they're listed separately and you want it mashed up together, put it under 1. It's all the same. But if I look here, the square root of 49 is just 7. The square root of 11, no perfect squares in there except for 1. So we just leave it. We've simplified all the perfect squares that we can. Now it's totally fine if you have a radical up in the numerator. It's not fine if you have a radical in the denominator. If only there was a way to fix that if that does happen. I don't know. We'll see. Here, if we square root each one, square root of 25 over square root of b to the 4th. Square root of 25 I know is 5. And the square root of b to the 4th is b to the 2nd. Look at that. All the square roots gone. It's all perfect. Just like you guys. Oh, right. Okay. All right. Look, square root of 144 is 12. Square root of 9 is 3. You can simplify 12 over 3. It's just 4. Or, if you want, you could divide 144 by 9 first. It comes out to 16, and then the square root of 16 is 4 that way. Same thing. Oh my gosh. All right, here we go. Look at that numerator. 25p to the 3rd. It's pretty much perfect. The 25 is perfect. The p to the 3rd is not. P squared is perfect, but then we'll have a leftover p. In the denominator, q squared, that's all perfect. So, square root of 25p squared is 5p. Root p. Our denominator, square root of q squared, is q. We've taken out all the perfect squares. There are no radicals in the denominator, so we're all gold, pony boy. All right, here we go. C. I can't simplify anything first, so we'll go ahead and go to the perfect squares. 75 I know is 25 times 3. The denominator, that is all perfect. 16t squared. Those are all perfect squares. So the square root of 25 is 5. 5 root 3. The square root of 16t squared is 4t. Your shoulders getting a little tired from all this math? All right. Oh gosh. Whew. Holy smokes. Here we go. 18 over 11. Now I could work on the 88. I think I said 18. I could work on the 88. It's like 4 times 22 or whatever. But you can also simplify this. 88 divided by 11 is just 8. It's like 8 over 1, but we're just going to make it root 8. All right? That's 88 divided by 11. And then we could break this down into 4 times 2. And that would give us 2 root 2. So if you can simplify it, I'd highly recommend doing that first. Here, think of what goes into 27 and 12. Imagine the square root's not even there. We just had to simplify it. 3 goes into 12 and 27. 3 goes into 12 4 times. 3 goes into 27 9 times. Look at the a's. We did this in the exponent unit. When you have the same base, you subtract the exponents when you're dividing. So a to the 3rd over a to the 1st, there's 2 more a's in the numerator. That would completely wipe out the a in the denominator. So if I just rewrite this now, in the numerator we have the square root of 4a squared. The denominator, all we have left is the square root of 9, and those are both perfect squares. The square root of 4a squared, 2a. Square root of 9, 3. NBD, no big deal. All right, we got 3 more of those. Here, I'm just going to divide them. I know 90 can divide by 5. It's 18. And then 18 is 9 times 2, 3 root 2. Now, I'm blasting through these because these are the ones where if you were in class, I would have you actually try these out. So again, pause and try them out, and then check in, make sure you got the same thing. I'd recommend it. If I simplify these, they're both divisible by 3. 48 divided by 3 is 16. 75 divided by 3 is 25. And those are both perfect squares. The square root of 16 is 4. Square root of 25 is 5. Here, 27 divided by 3 is 9. 9 over 1, right? And there are 2 more x's in the numerator. So the denominator would completely go away. And it's just the square root of 9x squared, which is just 3x. All right. Now, what if you have a radical in the denominator? What in the world can you do? Here's where that trick I taught you earlier about the square root of smiley face times the square root of smiley face can be a little helpful. You can alter fractions however you want, right? When we were adding fractions back in 4th, 5th grade, you multiplied them to get them to have a common denominator. So when you multiply a fraction, you multiply the top and the bottom, numerator and denominator. Same thing with the radicals. If you can't have a radical in the denominator, we're going to turn it into a perfect square, a number that we can square root. The easiest way that you can do that is to just multiply it by itself. Because remember, the square root of 5 times the square root of 5 would be the square root of 25, and the square root of 25 is just 5. So square root of 5 times square root of 5 is just 5. But if you do something to the denominator, you also have to do it to the numerator. So we're also going to multiply the numerator by root 5. And when you do 2 times root 5, don't make it root 10, because the 2 isn't in a radical. 2 times the square root of 5 is just 2 root 5. That's it. 2 root 5 over 5. You can't have radicals in the denominator, man. Last thing you would want to check is if you can simplify the numbers outside the radical, the 2 over 5, which you cannot. All right. On B, you have a couple options. You could break down the 8n with perfect squares. That'll work. I'd say let's hold off on that. Let's just do what we did on the first one. Multiply it by itself. Times root 8n times root 8n. In the numerator, they're both in the radical. 7 times 8n is 56n. Denominator, the square root of 8n times the square root of 8n is just 8n. No more radicals in the denominator. Now you do want to check, are there any perfect squares in the radical, which there are. 56, 4 goes into 56. It's 4 times 14, and the n is not perfect. So 4 times 14n. Now when we take the square root of that 4 up there, it's going to be 2 root 14n. So we have 2 root 14n over 8n. There are no more perfect squares. There are no radicals in the denominator. The last thing to look for is, can you simplify the stuff outside the radical? And you can, because 2 goes into 8. So 2 goes into 2 one time, 2 goes into 8 4 times. So we have 1 root 14n, which is just root 14n. The denominator, we have 4 times n, which is 4n. That's as nasty as these things are going to get for now. But you cannot have radicals in the denominator. So I would like you to try these 3. I'm going to go over them pretty quickly, but feel free to pause and actually give them a try. And 3 root 3 you can divide by 3. So it would be root 3 over 1, which is root 3. Let's see, that would give us 90t square root of 9, let's see, 3 root 10t over 18t And then 3 goes into 18 6 times, so root 10t over 6t. Last one we'll do times root 10 over root 10. That would give us root 70m over 10. And there are no more perfect squares than 70. And we're having fun.